Great. Great, fantastic, awesome. A very, very good evening to all of you. Achal, Aryan, Jannat, Guna, and all those who are present here for today's class. So today, this is a demo class for the basics of aircraft structures. You can also call it strength of materials, right? Some of you might have studied with the name of mechanics of materials or solid mechanics or mechanics of deformable bodies, whatever you might call it. Right? This is going to be a very interesting class, right? This is going to be very basic, right? So even though it is very basic, today's class, you'll not be able to understand the subject without actually going through this class. Okay? So it is very basic. It is very, very basic, but still, this class is so very fundamental and so very foundational, right? That if you understand this class properly, it is going to be very, very easy for you to decode the subject of strength of materials. So all of you ready to go? Please type ready if you're ready to go. Please type R in the chat box if you're ready to go. Please type R in the chat box if you're ready to go. Awesome, great. So as you can see on the screen, can you read the question that is on the screen? Yes, guys? Can you read the question on the screen? Will you be able to answer it? What is the stress at the points M and N? So this is a structure. Okay? This is a structure, right? So two-dimensional front view of the structure is given to you. And you can see there is a load P acting on the structure, right? And what is being asked? There are 2 points, M and N. Very, very simple question, right? What is the stress at points M and N? What is the stress at point M and N? Yes. You guys have studied, right? Strength of materials. And you guys know, most of you, okay? And I assume 100% of you know what is stress. No doubt we are going to study it. But this question is very, very important to understand, right? What exactly we are going to study. How many of you feel that the stress will be is equal to force divided by the cross-sectional area? So this is kind of a 3D bar, okay? This is kind of a 3D bar, okay? I'm just trying to show you how exactly it will look like in 3-dimensional view. Okay, this is kind of an isometric view, right? This is how the bar is going to look like, right? A rough diagram, okay? So if you're unable to imagine what exactly is going on, so there is a load P acting here, right? And this end of the bar is fixed. So I've taken 2 points here. This point is M, this point is N, right? So because of this force P, right, this is actually represented in 2D form. So what is the stress going to be at point M and point N? Tension, compression, N is going to be tension. Okay. To some extent, you are able to imagine, Guna, right? But not precisely. Yes, combination of bending stress is also a normal stress. Bending stress is also a normal stress, right? Combination of axial and bending, right? So the stress at point M, is going to be, force divided by area minus moment divided by Z, M by Z. And stress at point N is going to be force divided by area plus M divided by Z, right? So this is a term that you have already seen, right? You know basically you must have studied it in your college, right? P divided by A stress. So what exactly is this term? And how did it come up here? So this is what you need to understand. This is what you need to understand. And in today's lecture, you'll get an overview. In today's lecture, you'll get an overview why the stresses at point M and N are so different than what you have actually studied earlier. Why the forces at point M and N are so different than what you have studied earlier. You might have studied it as if P by A, some of you are saying yes, right? This combination of normal and bending, right? But we need to understand it even better, right? So this before getting into this point of stress, okay, before getting into stress, I want to tell you something. Okay, I want to tell you something, okay, about mechanics. Okay, it's a very basic fundamental. Okay, it is going to be very basic fundamental. Still, it is going to be very important. Okay, quickly we'll go through. Okay, quickly we'll go through the concept of mechanics, right? So, if I ask you to define mechanics, which you have studied from class, in fact, from class 9 onwards, right? From class 9 onwards, we start studying mechanics. And when we get into 10+1, right, we study mechanics in great detail, right? So if you ask you what is mechanics, not a book's definition, though, right? I will call mechanics a study of forces and its effect. And its effect. Study of forces and its effect. So what is the force acting and what is the effect of it? Don't worry, I'm going to show you. Okay? I'm going to explain it to you because this understanding is very important if you want to understand the subject of structures. So I can classify mechanics into different parts. There are many different types of mechanics. For example, one is engineering mechanics. You have heard the name, yes or no? Please type yes if you know what is engineering mechanics. Right? One subject you have is mechanics of materials. Mechanics of materials. We also call it solid mechanics. We also call it mechanics of deformable bodies. We also call it as a subject of strength of materials. And this is basically basics of the structures, right? Aircraft structures, right? So different authors have titled this differently, right? Some authors have titled it strength of materials. Some have titled it MODB, mechanics of deformable bodies, solid mechanics, mechanics of materials, right? Then there is a subject known as fluid mechanics. You see, all of these are mechanics, right? Then civil engineers, they study a subject known as soil mechanics. If you have any friend from the civil engineering, there's a very important subject for them, right? And they have even more further classification. We'll not go into that, right? But you see, all these are mechanics. So what exactly is happening? Okay, whenever I'm studying engineering mechanics, the object, the system on which the forces are acting are rigid. What is the meaning of rigid bodies? Do you know what is the meaning of rigid bodies? Body that does not deform. Very good, right? So whenever you are applying a force on a body, if the body does not deform, right, means its shape or size does not change. Shape and size does not change. It is called a rigid body, right? When we are studying engineering mechanics, all the bodies are considered to be rigid. And that is why when you apply a force, whenever you are applying a force, what is the effect? The effect is acceleration. And that is what we find out. How much force is acting and what is the acceleration produced. This is the basics of engineering mechanics, isn't it? Right? How much force is being applied, and what is the acceleration of the body. Now, when you come to solid mechanics or strength of materials, or as the name suggests, mechanics of deformable bodies, here the bodies are considered to be deformable. What is the meaning of deformable bodies? What is the meaning of deformable bodies? That's true, Achal, right? They have shear stresses, but stress is secondary, right? The main is the body they can deform, right? Opposite of rigid. On application of force, the body is deformed, means shape and size changes, right? And because the shape and size changes, stresses are induced. We'll see that, okay, in our first class. Because the shape and size changes, the stress is induced. And one of that stress can be actually shear stress. We'll see. Not always. There can be cases where there is no shear stress, right? What is fluid mechanics? So basically, in strength of materials, the subject that you are going to study, right? Whenever forces are acting, what is the effect? The effect is change in shape and size, right? And because of this, stresses are induced. Because of change in shape and size, the stresses are induced. So what force, when you are applying, what is the effect? Change in shape and size. What is fluid mechanics? Whenever the forces are acting on fluid, be it gas or liquid, right? Whenever forces are acting on a fluid, what is the effect on that fluid? The fluid flows, isn't it? Whenever there is shear stress on a fluid, the fluid will start flowing. And when you study this combination, what forces are acting and how is the fluid behaving, what is the effect of fluid, that is classified under fluid mechanics. Similarly, the civil engineers, when they start building a structure, right, the civil structure, right, now the whole structure, the load of the whole structure will be borne by the soil, isn't it? Whenever you're building a structure, you build it over the soil. The house you are right now sitting and going through this online lecture, it is built on soil, isn't it? So when you build a structure, the structure is going to apply force on the soil. So what you have to do, first you have to study the soil. What is the effect on the soil? If you apply forces on the structure, will it be able to withstand the forces? How's the soil going to behave? Right? That is nothing else but soil mechanics. Right? And in aerospace, basically, this is also the strength of materials. So mechanics of deformable bodies is also called you can say, the basics of structures, because what you need to see, whenever forces are acting on different forces, be it the gravitational force, be it the forces because of the flow of air, the drag, the lift, okay? So how is the structure going to behave, your aircraft structure going to behave? That is what we are going to study in the aircraft structures, and the basics you have developed from here, right? So I hope you have got an idea. You are just studying an extension of mechanics here, right? So everything basics comes from mechanics, and we are just keeping on building it, right? We are going to study mechanics of deformable bodies. Whenever forces are acting on deformable bodies, how the deformable bodies are going to behave. Basically, stresses will be induced, and what will be those stresses, how to calculate those stresses, and how to make sure the material, the structure does not fail under this stresses, right? So this is example of that. Okay? This is an example of this whole study. So whenever a force is applied, what is the effect on the points M and N? There are stresses of this much magnitude on this points M and N, right? So guys, tell me, first what you should know. Should you study the forces first, Or should you study the effect first? What should you know first? To understand this subject properly, which is the topic, you should actually study first. Should it be the forces or the effect? Aryan is saying forces. I'm not getting much answers from others. Yes, guys. What do you feel? Should you study the effect first or should you study the forces first? Yes, great. We have to study the forces because these are the forces which are producing the effect. Right? So let us start with forces. Let us start with forces. Before understanding the forces, right, we'll have to understand a few basic things, right? Few basic exercises which will help us to understand the forces even better, right? So you see this. This is a basic element, okay? And I'm going to tell you four different exercises which are very, very core to your structures, the study of structures, aircraft structures. Right? Very, very core, very, very important. And you're going to have this exercise each and every time you try to solve a problem. Right? So the main axis, okay, the main axis is known as the longitudinal axis. Okay, even before longitudinal axis, I'll try to show you something. This is the cross section. What is this? This is the cross section. Right? Cross section, right? Okay, you can call it CROSS section, not a problem, right? What is the centroid of a cross section? The midpoint of the cross section is a centroid. Now, my dear friends, I'm going to draw three axes. Please look at the board very carefully. I'm going to draw three axes which are passing through this centroid. I'm going to draw three axes which are passing through this centroid, right? This is axis number one. Right? I'll call it XX. This is axis number two. I'll call it YY. Don't underestimate this axis. These are very, very important axes. And I'm going to draw another axis, which is Z axis. Now, all these three axes, XX, YY, and Z, are passing through the centroid. Yes or no? Type Y for yes. Type Y for yes. All these axes, XX, YY, and Z, are passing through the centroid. Yes or no? You can type yes for Y for yes, N for no. Right? Because they are passing through the centroid, they will be called centroidal axis. All these three axes, XX, YY, and Z, are known as centroidal axis. Why centroidal axis? Because they are passing through the centroid. Now, if you can see properly, there are two axes which are parallel to the centroid, XX and YY. Can you see these are parallel to the cross section? And there is one axis, Z, which is perpendicular to the cross section. Right? Axis YY, can you see this is parallel to the cross section? Axis XX, it is parallel to the cross section. Whereas the Z axis is perpendicular to the cross section. If you agree, type R for right. If you agree, type R for right. Right? So this N, out of this, XX is horizontal. So it is known as horizontal centroidal axis. YY is vertical. And so it is known as vertical centroidal axis. And Z axis is very, very important axis, which is known as polar axis. It is known as polar axis, which is perpendicular to the cross section. Now, let me ask you a question. How many cross sections do you think this member is going to have? This member, how many cross sections do you think this member is going to have? How many cross sections you feel this member is having? Yes. How many cross sections are there? 6? 8. Good thinking. Okay, good thinking. Okay. But the cross section, okay, the cross section in strength of materials will always be perpendicular to the length. Very nice. Infinitely many. Very nice, right? So first of all, understand what is a cross section. Cross section is something which is perpendicular to the length. Okay. So the cross section will be always situated this length, this way. This is a cross section. Similarly, this is going to be a cross section. All the other sections will be known as oblique plane. We'll study it later on. We'll study it later on. All these are what? All these are different cross sections. All these are different cross sections. Getting my point? Because cross sections are perpendicular to the length. Okay, we'll study it later on. Now, all these cross, so there can be infinitely many cross sections. There can be infinitely many cross sections. Wherever you cross it, you'll get a cross section. Wherever you cut it, you'll get a cross section. Now, all these cross sections will have centroids. Yes or no? All these cross sections will have centroids. Yes or no? All these cross sections will have centroids, right? Now, if you draw a line passing through all the centroids, if you draw a line passing through all the centroids, this line is going to be called the longitudinal axis of the member. Longitudinal axis of the member. The longitudinal axis, as the name says, it is along the length. The longitudinal axis, as the name says, it is along the length. Is the longitudinal axis of the member. So all of you do remember all these 4 axes because these are going to be very, very important, right, when you study the subject of strength of materials. Now let us come to different types of forces. Okay, let us try to see different types of forces. Okay, so this member, I am drawing few forces. Okay, I'm going to draw few forces on this member. Right, you can see this force. I'm calling it P1. I'm drawing another force, P2. I'm drawing another force, P3. Very good question, Guna. I was expecting this question. I'll solve your query. P4. Okay. Let us go back to your query. Now see, the polar axis is the axis of the cross section, whereas the longitudinal axis is the axis of the member. I'll show you how. Right? Let me draw a small diagram here. Okay, 2D diagram. Let me say this is the member. You bend the member, this is the member. Right? Now, if you try to see the polar axis, wherever you choose a cross section, you'll get a polar axis. If you choose the cross section here, this will be the polar axis. If you choose the cross section here, this is the polar axis. If you choose the cross section here, this is the polar axis. If you choose the cross section here, this is the polar axis. So all the cross sections will have different polar axes. Right? But if you talk about the longitudinal axis, the entire member will have only one longitudinal axis, and this is the longitudinal axis. Getting my point? The red one represents the longitudinal axis, only one longitudinal axis for a member. But all the blue ones are the polar axes. Wherever you draw a cross section, you'll get a polar axis there. Clear? Great. That is what you need to ask questions. That is why you are here. So I'm drawing another force, P5. I'm drawing another force here, P6. Can you see this? And I'm drawing another force here, P7. Now let me tell you, okay, P1, P2, P3, P4, P5, P6, P7. Even if their magnitude is same, Let me say all the magnitudes are, say, 10 kilonewton, all the forces, P1 to P7. But the effect these forces will produce on the member, the effect is basically the stress, is going to be different for all the forces. P1 is going to produce different stress. PT is going to produce different stress, even though the magnitude is same. P3 is going to produce different stress, P4 is going to produce different stress, P5 is going to produce different stress, P6 is going to produce different stress, and P7 is also going to produce different stress. Because the magnitude might be same, but because these forces are different. So that is exactly what we are going to learn in today's class. How to identify these forces. So let us start. Let us start identifying the forces. Now I'll call them loads. These forces are nothing else but loads. Why? I'm calling them load because these forces are not producing any movement. Okay? And whenever they're not producing any movement, right? Means the forces are not producing any motion. The forces are producing only deformation. So whenever the forces are producing only deformation, we can also call them loads. FORCES. Right? Whenever the forces are producing only deformation, we can also call them loads. So this is how we call them, right? We can also call them loads, right? So the loads can be classified into normal loads and shear load. My dear, let me tell you, these are not stress, these are loads. These are not stress. We are going to see later on if there is a normal load, what will be the stress? If there is a shear load, what will be the stress? We are going to link it later on. But for now, these are simply loads, right? So if I say normal load, right? What are normal loads? Normal loads are those loads which are perpendicular to the cross section. Can you look at this diagram and tell me which of the loads are normal loads here? Normal loads are those loads which are perpendicular to the cross section. Now, can you please look at the figure and tell me which of the loads are normal loads? Yes. See, if you are into the field of engineering, that too in aerospace engineering, right? You have to develop your imagination skills, right? You have to develop your skills, the skills where you look into a figure and able to extract the things. It's very, very clear. Can you see that? Yes, come on. Aryan has typed. Jannat, can you see? It is P1, P2, and P3. Can you clearly see that P1, P2, P3 are normal to the cross section, whereas P4, P5, P6, and P7 are parallel to the cross section? Type R if you have understood. Type R for right if you have understood. You can clearly see there are three normal loads here. So normal loads are those loads which are perpendicular to the cross section. So what are the normal loads here? The normal loads are P1, P2, P3. Again, let me tell you, these are loads, not stress. Similarly, shear loads. Shear loads are those loads which are parallel to the cross section. Can you identify? Can you identify which of the following loads are shear loads? Come on. Yes, you can do it. Come on, guys. Don't hesitate, right? You have, if you are into class, you will have to ask questions, you'll have to type. Don't be afraid of making mistakes, because only when you correct your mistakes, it is when you'll improve, isn't it? If you hide your mistakes, you'll not be able to improve yourself. Very, very important. Yes, P4, 5, 6, 7. Guna, What about 6 and 7? These are also parallel to the cross section, isn't it? These are also parallel to the cross section, isn't it? Right? So P4, P5, no doubt they are parallel to the cross section. P6 and P7 are also parallel to the cross section, right? Right? So how many shear loads are there? There are 4 shear loads, P4, P5, P6, P7. Please type U if you have understood. Please type U if you have understood. Or if you have any doubt, you can type it. Come on. I need more number of replies. I need more number of replies. Don't hesitate. Okay. So it is simply angular loads. Okay? Angular loads can be actually divided into components. If a load is acting at an angle, you can always resolve it into components, and one component will be perpendicular to the cross section and one component will be parallel to the cross section. So it is basically a combination of both. Right, Aryan? Right, Aryan? Yes. Neeraj, we are talking about loads. Okay? We are talking about loads. Loads can be classified into two parts: normal loads and shear loads. Okay? Normal loads are those loads which are perpendicular to the cross section, and shear loads are those loads which are parallel to the cross section. Okay? So if you see, Neeraj, I want you to see on the screen. You can see there are 7 loads out here. Out of the 7 loads, P1, P2, P3, can you see these are perpendicular to the cross section? P1, P2, P3, these are perpendicular to the cross section. Yes, you can speak if you want, Neeraj. Okay. So P1.
Yeah, I see on the screen. Like I understood the concept actually.
Okay.
Yeah.
Great. Fantastic.
Yeah.
If you have any doubt, Neeraj?
No, I do not have any doubt actually.
Great. Awesome. So now let us go on to classification of normal loads. Right? Now the normal loads, they can be actually classified into two types: axial and eccentric axial. Now the normal loads, if they are passing through the centroid, if the normal loads are passing through the centroid, they will be called axial loads. Why axial? Because if they're passing through the centroid, they are also passing through the longitudinal axis of the member. Right? Can you look at the diagram and tell me which of the following load is an axial load?
So in the I mean, you are asking about in the normal load section or the shear load? Like in the normal loads, P1 will be the axial load.
Exactly. So I'm first telling you about the normal loads. Right? We're first
Yeah.
discussing normal loads.
Yeah.
Okay. We'll come to the shear load.
So
Yeah.
P1 will be the axial load.
Right. Exactly. Right. You can use the chat box also. Is the chat box available?
Yeah.
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 Great.
Yeah. It's available.
Great. Fantastic. Awesome. And if the normal load is not passing through the centroid, it will be called as an eccentric axial load. Eccentric, the meaning of eccentric is basically not passing through the centroid, right? So can you just figure out which of the loads are eccentric axial load, EAL? Which of the loads are eccentric axial load? Can you figure out from the figure? P2 and P3, right? So P2 and P3 are nothing else but eccentric axial loads. Okay? Now let us come to shear loads. Shear loads are those loads which are parallel to the cross section. If the shear load is passing through the centroid, it will be known as transverse shear load, TSL, transverse shear load, if this is passing through the centroid. Can you look at the diagram and tell me which of the following are transverse shear load, TSL, shear load and passing through the centroid? You can clearly see it is P4 and P6. It is P4 and P6. Right? Great. P4 and P6. Keep on typing, guys. Neeraj, come on. P4 and P6. Right? These are loads which are passing through the centroid. Right? You can see this is parallel to the cross section and also passing through the centroid. Right? And if the shear load is not passing through the centroid, it is known as eccentric transverse shear load. In short form, we'll call it ETSL. Can you look at the diagram and tell me, Neeraj, which of the following loads are ETSL? Not exactly 8, it's 5, right? You're correct. You identified it correctly. It's a typo error. P5 and P7, right? So P5 and P7, you can clearly see there are shear loads, but they are not passing through the centroid. Right? Now, as I told you, okay, all these loads are going to produce different effects. Right? So whenever they might be of the same magnitude, but all the loads are going to have the same different kind of effect. For example, let me give you an idea. Axial loads will only produce tension or compression. Tension or compression. In short, I'll say T or C. Axial loads will produce only tension or compression. Whereas eccentric axial load, they will produce tension or compression. And apart from this, they will also produce constant bending. Constant bending. Yes, because the directions are different. Right? They will produce tension or compression plus constant bending. Now, if it is a transverse shear load, you'll see all these things later on. Okay? If it is a transverse shear load, they will produce tension or compression. Okay? They'll produce tension or compression, but or basically that is basically a part of bending. Right? Plus variable bending plus shear stress. Right? Whereas eccentric transverse shear load, it will produce twisting plus variable bending plus shear, direct shear. You see, the magnitude of the loads might be same, okay? But the effect of all the loads will be different. Axial loads will produce either tension or compression. Eccentric axial load will produce tension or compression, and plus there will be a constant bending. Transverse shear load will produce a variable bending plus direct shear. Whereas eccentric transverse shear load will produce twisting, variable bending, and direct shear. And that is why it is very, very important that we first understand what kind of load is acting. Because only when we understand what is the type of load that is acting, then we'll be able to produce what is the effect the load is going to produce. Right? Is it clear till now? Is it clear till now? We are going to see all these things in our classes, okay? To whatever extent possible. We are going to decode each and everything. We are going to see what is the effect of axial loads, eccentric axial loads, transverse shear load, and eccentric transverse shear load. Right? Okay. Now, let's see how much you have understood. Okay? It's simple exercise. Let us see how much you have understood. So now, as you can see on the figure, there is a member, right? And there are three types of loads acting on the member. Right? I will try to draw a 3D member for this so that you can actually have a better understanding. So this is the kind of member. Okay. I'll draw a 3D member for you so that you have a better understanding of how a member looks like. For simplification, I have sorted this. So this is the member. Okay. One single member, one single frame, you can say. This end is fixed here. Okay. And I have simply represented the longitudinal axis here. See, A, B, C, D. I have simply represented the longitudinal axis here. Right? I've just shown only the longitudinal axis. Okay. This is the longitudinal axis AB. Right? Then I've shown the longitudinal axis BC. Right? And then I've shown the longitudinal axis CD. Okay. A, B, C, D. And there are three forces acting on the ND. There are three forces acting on the ND. Right? So what are these three forces? There's a force PQR. So the P is acting like this. Let me mark with blue. Let me make it large. Extra large. This is the load P. Okay. And as I said, you have to use a little bit of imagination here. Okay. Then you have a load Q, which is acting in the downward direction. Right at this point. Right. And then we have a load R. So what is the meaning of cross? Who can tell me what is the meaning of cross? Inside the screen, right? Cross means the load is going into your screen. And if I represent a load, because this is a 2D view, okay, I cannot show the load going into the screen. This is the isometric view, you can say. Here, you can actually see the load R is actually going into the screen. So here I can show the load R like this, not a problem. To some extent, you'll be able to understand, right? But in a 2D view, I'm going to represent it using a cross. What is the meaning of dot? If I represent the force as a dot, what is the meaning if I represent the force as a dot? The force is coming out of the plane. The force is coming out of the plane. Now, I want you to take 2 minutes to fill up this table, right? So P, I'll help you out with the first. P, let us start with CD. Let us start with CD. So P, load P. Can you tell me what kind of load is P for CD? Is it AL? There are 4 kinds of loads possible. Axial load, eccentric axial load, right? Transverse shear load, and eccentric transverse shear load. I want you to figure out P is going to be what kind of load for the member CD. Can you see this? It is definitely along the longitudinal axis, right? Clearly, you can see it is an axial load, AL. Now, can you see Q? What do you think Q is for the member CD? Yes, I want all of you to answer. All of you to answer. Don't be afraid of making any mistakes. It is a Yes, Neeraj, it is going to be a transverse shear load. Right? You can clearly see it is parallel to the cross section and also passing through the centroid. Load Q is parallel to the cross section passing through the centroid. So transverse shear load. P, it is perpendicular to the cross section passing through the centroid to axial load. So this is a TSL. TSL. Now, can you figure out what is R for the member CD? Can you figure out what is R for the member CD? It cannot be both, right? It has to be only one. Only for the member CD. So this is the member CD. Now is R acting? R is acting this way. It's going into the plane, right? It's parallel to the cross section, right? You can see it is going into the plane. This is the member CD. R is going into the plane, right? Means it is parallel to the cross section. At the same time, it is also passing through the centroid of the cross section. So it is going to be TSL. Please type U. Yes, like P6 in the diagram. Okay. If you look at this diagram, it is like P6, but only the direction is the opposite. Okay. Please type U if you have understood. Please type U if you have understood. Great. Now I want to figure out these three loads PQR for the member BC. I want you to figure out this member's PQR for the member BC. Come on, you can do this. There is nothing like bending. Okay, first of all, you have to understand, you have to classify it in this form, right? Then we will later see what is the effect of axial load, what is the effect of eccentric axial load, what is the effect of transverse shear load, what is the effect of eccentric transverse shear load, right? So there is no bending here, at least till now, right? No doubt. Apart from axial load, all three will produce bending. Okay. The load P, can you see that the load P is going to be perpendicular to the parallel to the cross section of BC? Yes or no? Right? And it will also pass through the centroid. You can see this is the load P. If you extend it, it is parallel to the cross section of member BC. At the same time, it is also passing through the centroid. At the same time, it is also passing through the centroid. Right? So it is going to be a TSL, transverse shear load. Q for the member BC. What is load Q for the member BC? What is load Q for the member BC? Are you sure? It is an eccentric axial load. Eccentric axial load. Now, how to see? Now you see, load Q for sure is perpendicular to the cross section. Are you yes or no? For member BC, it is perpendicular to the cross section BC. Yes or no? The only thing is that it is not passing through the centroid. Can you say this? This is perpendicular to the cross section of BC. The only difference is that it is not passing through the centroid. So a load which is perpendicular to the cross section and not passing through the centroid is eccentric axial load. R for the member BC. R for the member BC. Is it TSL or ETSL? Okay, R is parallel to the cross section, that is you can clearly see. It is parallel to the cross section, right? Is it passing through the centroid? No. It is parallel to the cross section. Na, yaar. Come on, you can see this. This is the cross section. If you take a cross section, you can see R is parallel to the cross section. Right? Yes or no? Right? The only difference is that it is not passing through the centroid. So it is going to be ETSL. ETSL. Right? Now let us figure out with AB. Let us figure out AB for the member AB. Come on, you can do it. What is load P for the member AB? What is load P for the member AB? Is it TSL, Jannat, Harsha? Okay, let us figure out. Okay, little bit of imagination will be required. This is the cross section. Okay. Now, what do you think? Load P is parallel to the cross section or perpendicular to the cross section? What do you feel? Load P, is it parallel to the cross section or perpendicular to the cross section? It is perpendicular to the cross section, but it is not passing through the centroid. Right, Jannat? It is a EAL, eccentric axial load. Right? What is Q for the member AB? What is Q for the member AB? Yes, Q and R. Try to figure it out. Yes. Q for the member AB is going to be a TSL. Right? Let us see how. So if you see Q, right? If you simply extend it, okay? If you simply extend it, okay, you can clearly see it is not just parallel to the cross section, it is also passing through the centroid. Right? Sorry. You can see it is not just parallel to the cross section, it will also pass through the centroid of the member AB, the cross section of member AB. Right? Right? So this is parallel and also passing through centroid. You have to do a little bit of imagination because this, if you draw this, it is going to pass through the longitudinal axis. If you draw the member, okay, if you draw the member, it is also going to pass through the centroid of the member AB, right, of any cross section. So this is going to be a TSL. What is R for the member AB? What is R for the member AB? It is a ETSL. The ETSL. Why? Again, if you clearly see, R is definitely parallel to the cross section, but it is not passing through the centroid. It is parallel to the cross section, but if you see, it is not passing through the centroid. Right? So all these forces are going to have different effect on the member AB. Now, if you go back to the question, the first question that we have seen, okay? So can you now tell me what kind of load is P for the member AB? What kind of load is P for the member AB? What kind of load is P for the member AB? Is it axial or eccentric axial load? It is eccentric axial load, right? It is eccentric axial load, EAL, right? So eccentric axial load will produce tension or compression, either tension or compression, and along with it, it will also produce bending stress. Right? Now, if you see this, because of this load, okay, these two members will be under. If you see axial, okay, axial stress, okay, axial stress, it will be compressive in, sorry, tensile in nature. To see if it is tensile in nature, this is P by A, right? And it is going to produce a bending, because of which there will be compression here and tension here, right? Bending stress is given by M by Z. We'll see this later on. Bending stress is given by M by Z. And on the top fiber, the bending stress will be positive, sorry, compressive. And on the bottom fiber, the bending stress will be compressive and tensile. So basically opposite to each other. So I'll write it as plus minus M, right? At point M, axial stress is tensile, bending stress is compressive. At point N, axial stress is tensile, whereas bending stress is also compressive. Okay. Later on, after you have done say 50 to 70% of the classes, you'll be able to understand this properly. Okay. Because it is an eccentric axial load, it is going to produce axial stress plus bending stress. I'll call it axial stress. Axial stress plus bending stress. Axial stress is P by A, which is tensile. Right? Bending stress is compressive on the top, tensile in the bottom. So I've written it as plus minus. At point M, it will be P by A minus M by Z. At point N, it will be P by A plus M by Z. Right? But yes, the theory that you have learned till now is not enough to decode it completely. We'll have to understand what is bending stress, right? How to calculate it, what is axial stress, and slowly, step by step, we are going to understand, right? So what is the future course of lectures going to be like, right? First, we'll understand what is axial stress, right? How to calculate, what are different types of problems that are asked from this section, right? Then we will move on to bending. We'll understand bending, and then we will solve questions from EAL, right? Then we'll see what is the effect of TSL, very, very important, right? Because all the deflection of beam chapter, right, it is based on TSL. And then ETSL also. In between, there are two different chapters that are going to come, right? One is bending couple and one is going to be twisting couple. Okay, clear? Now, before ending, I'll just like you to tell something. Before ending, I'll just like you to tell something about the gates preparation. Right? So I started preparing for gate after my college. Right? I started preparing for gate after my college. And after I prepared, right? I understood that the funda is not about only hard work, but it is also about smart work. If we can work a little bit smarter, right, we'll be able to score good marks easily. Right? And what is that smart work, right? So if you see even the subject of structures, or say, let me say uh, um, uh, for this subject, if you consider the strength of materials, right, all the topics are not equally distributed. So this is the basic syllabus, right? But if you see 50%, more than 50% of the marks are asked from these chapters, right? Because you have limited time with you. So these are the chapters which are must. Questions from principal stress are asked every exam, right? Questions from buckling, elastic stress are very, very important. There are some chapters from where around 30% of the marks are asked, right? Torsion, very important. Almost every year, say alternate year questions are being asked, right? Yield theory is very, very important, right? And then later on, if time is left out, then you can actually focus on the tier 3 subjects, topics, right? Which includes pressure vessels, plane stress, compatibility, nonlinear stress graphs, right? But the thing is, you have to understand, because your time is limited, okay? It is not a very good idea to give equal importance to all the topics. What I mean to say, study more of the more important topics. Okay? Practice more questions from the tier 1 topics. Slightly give less amount of time to tier 2 topics. And then at last cover up the tier 3 topics. Right? And this is the pattern that you need to follow for all the subjects. If at all, right, in the limited time, if you want to score the maximum marks, so your first priority should be to cover up the tier 1 topics of all the subjects, then tier 2 topics, and at last you can focus on tier 3 topics, right? So for example, let me say fluid mechanics and say strength of materials. Now, to cover up the tier 3 topics of strength of materials, don't compromise the tier 1 topics of fluid mechanics. Getting the point? Right? Suppose you have 10 hours of time, okay, to complete the tier 3 topics of strength of materials, right? And you gave 6 hours. And you give just 4 hours to the tier 1 topics of, say, strength of fluid mechanics, or say gas dynamics, it was a mathematics. It is a very, very bad strategy to crack the GATE exam, right? So you must have a clear idea of what you need to study, how much time you need to give, because that smart study is what is going to help you in securing a great rank in your exam. That's all for today. Thank you. Dinesa, are you there? Any questions, guys? You want to ask me any questions, you can ask.
Yes, sir, I am there.